This is going to be part 2 of section 3.6, forced oscillations and resonance. In a previous video, we analyzed undamped motion of spring mass systems where we had an external force, capital F of t. This is going to be part 2, forced oscillations with damped motion. So let's get started. We already identified our differential equation that's going to model this mass spring system with the external force F of t. And recall that we are only going to consider functions of the form cosine omega t and sine omega t. So that's what we're going to be considering for that F of t function. So we've already covered pages 1, 2, and 3 in the previous video. We'll get started here at the top of page 4. Again, we're assuming damped oscillations. So now instead of assuming that C equals 0, we have a non-zero damping constant, which is going to bring in this first derivative term. Otherwise, the differential equation is the same as before. So thinking back to section 3.4, we had talked about when we were finding complementary functions for these mass spring systems, there were 3 different possibilities. Mathematically speaking, those possibilities come from whether your roots of your characteristic equation are real and distinct, real and repeated, or complex conjugate pairs. The book discussed those as overdamped, underdamped, or critically damped. However, what we want to focus on here is that as x approaches 0, or excuse me, as t approaches infinity, the complementary function is approaching 0. So in other words, the complementary function is dying out. As time increases, that function has less and less of an impact on the output of the overall solution. Because of that, we call x of c the transient solution. So again, thinking of the fact that it dies out, so it doesn't make a large impact, hence the word transient. The particular solution is the one that really governs the overall function or behavior of the general solution x, and we call that the steady periodic solution. So I like to remember that the particular solution has that subscript p, and steady periodic also has that p. So that's how I remember that the complementary function matches with transient and that particular solution matches with the steady periodic. What we'll see is our steady periodic will typically be written as a sum of sine and cosine, but as usual, the book will request that we reduce that to a single cosine function. C and alpha were as given above. C is the square root of a squared plus b squared, and alpha is some shift of either 0, pi, or 2 pi plus tangent inverse of b over a. So let's take a look at our first example of damped motion here. Notice that we only want to find the steady periodic solution here. We are not finding an overall solution where we're summing the complementary and the particular solution. We just want the steady periodic. And just to remind you, that is the same as the particular solution. All right, so let's take a look here at this differential equation. We're going to start by considering the associated homogeneous dE by equating the right-hand side to 0. The characteristic equation that's associated with this dE is r squared plus 3r plus 5 equals 0. That is not going to factor by hand, so let's throw it into the quadratic. -3 plus minus radical 9 minus 4ac is going to be 20 all over 2. So we have a rather ugly answer here with the square root of 11 involved. So we have a complex conjugate pair. We can now write out our complementary function, which is also known as our transient function, to be e to the -3/2 t times c1 cosine of root 11 over 2t plus c2 sine root 11 over 2t. All right, so here's our complementary function. We're going to utilize that when we compute the terms and identify if we have some duplication. So now let's take a look at f of t, which is -4 cosine 5t. All right, so we can now list out our terms. As usual, we're only going to get two terms because cosine, when we take its derivative, gives us sine, and then we just keep jumping back and forth between the two. So we have cosine 5t and sine 5t. Again, we want to look back up at our complementary function, and we recognize that there is no duplication in this case. So that means we're going to use Rule 1 from section 3.5. That is, we'll take a linear combination of those terms. So our guess for the particular function, which is also known as the steady periodic function in this case, is going to be A cosine 5t plus B sine 5t. All right. So they had asked us to find the steady periodic solution, and we want to get down to a single cosine function. So in order to do that, we need to calculate the coefficients a and b, and then condense it to a single cosine function. So how do we find the values for a and b? The particular solution is a solution of the non-homogeneous dE. So as such, we want to plug it back into that original equation right up here. So I need to first calculate the first and second derivative, and then I'll be ready to plug it all in. So let's calculate the first derivative. I get a -5a, whoops, not cosine, but now sine 5t plus 5b, goodness, cosine 5t. And now the second derivative, I'm going to have negatives in both terms. -25a cosine 5t minus 25b sine 5t. So now we have all of the pieces we need to plug it into that original dE. I'll start by taking the second derivative. Adding it to 3 times the first derivative. And then finally adding it to 5 times the original. And all of this needs to equal a -4 cosine 5t. So next what I want to do is I want to combine like terms. So I'm just going to highlight all of my cosine terms to make it easier to add them up. So my coefficients on cosine are going to be a 20a plus 15b cosine of 5t. And now the remainders are sines, so let me add those up. And I just noticed one error. I left off my b right here, so I'm going to add that in red to call it to your attention. All right, so now let me add up all of my sines. I have a -15a and a -20b. And those are all the sine of 5t's. And then of course I just have a -4 cosine 5t, 0 of the sines on the right-hand side. So now let's equate coefficients. The coefficients of the cosine terms are a 20a plus 15b equals -4. And the coefficients for the sine term is -15a minus 20b equals 0. So we have a system of two equations and two unknowns. At this point, you guys are welcome to throw this into a matrix and utilize your graphing calculators to solve. I'm going to go ahead and solve this by hand. So let's take a look at the second equation. I have negative 15a equals 20b. So I can say that a is equal to negative 4/3 b, and then I'm going to plug that expression back into the first equation. So I have minus 20 times my expression for a plus 15b equals negative 4. So that's 80/3 b plus 45/3 b is negative 4. So I have 125b equals negative 12. So b equals negative 12 over 125. And I don't believe that's reducible. So I'll leave that as is. And then of course, just plug this value to solve for a. So a is a negative 4 over 3 times a negative 12 over 125. So I get a positive 16 over 125. So I've successfully solved for my coefficients a and b. Let me now write out what my current steady periodic function is. I have 16 over 125 cosine of 5t minus 12 over 125 sine of 5t. All right, so at this point you have a solution for the steady periodic function. However, we'd like to reduce this to a single cosine function. So again, c is the square root of a squared plus b squared, which is going to be, I'm going to just pull that 1 over 25 out front, the square root of 16 squared plus 12 squared. All right, and so that comes out to 20 over 125, which reduces to 4 over 25. So there's our amplitude there. And then we'll also note that A is positive and B is negative. So our alpha becomes 2 pi plus tangent inverse of B over A. So I get, what is it, negative 12 over 16 reduces to a negative 3/4. And so then finally, I say that my steady periodic function is my C value, 4 over 25, cosine of, we still keep the same weight in between there, 5t, and then I'm just going to write minus alpha, where I'll include alpha in my final answer here. All right, and so that concludes this first example, problem number 8, finding the steady periodic function. All right, our next example is going to be the full-blown initial value problem. So not only do we want to find the steady periodic function, but we also want to add it together with the complementary function or the transient solution in order to find the overall solution for the DE. So let's move forward here. All right, so they kind of do break it up. We want to first find the steady periodic function, and then we also want to find the transient solution. And again, the key difference here is that we're working with initial conditions, which is going to allow us to solve for those coefficients in the complementary function. So let's start as we always do. Let's find our characteristic equation that's associated with the homogeneous DE. So that's going to be r² plus 6r plus 13 equals 0. We'll use the quadratic equation again. -6 plus or minus 36 minus 4 times 13. So that's 12, carry the 1, 52. All over 2. So let's see. 52 minus 36 is, what is that? 4 to get up to 40 plus 12, 16. So that gives me a -6 plus minus 4i over 2, or -3 plus minus 2i. So now we can write out the transient solution, which is an e to the -3t, c1 cosine 2t plus c2 sine 2t. All right, so there's the setup for our transient solution. And then from here, we would like to look at our f of t function. And our terms that we'll get here is a sine of 5t and a cosine of 5t. So again, we want to compare that to our complementary or transient solution. We do not have duplication. So we move forward by setting up our particular function, also known as our steady periodic solution, as the sum of our two terms. All right. So now we want to move forward with solving for those coefficients. Let me find my first and second derivatives. So the first derivative here is 5a cosine 5t minus 5b sine 5t. The second derivative is a -25a sine 5t minus 25b cosine 5t. All right, so plugging it into the original DE, I have the following. -25a sine 5t minus 25b cosine 5t. Now 6 times the derivative gives me a 30a cosine 5t and a minus 30b sine 5t. And then finally, I want to add 13 times the original steady periodic function. And this all is to equal 10 sine of 5t. So again, let me go ahead and just highlight all of my sine terms so that I can quickly group them together. -25 plus 13 is a -12a. Minus 30b sine 5t. And now I'll group the cosines. We have 30a and a -12b. All right, so now we're ready to equate coefficients. For the sine terms, I have a -12a minus 30b equals 10. And for the cosine terms, I have 30a minus 12b equals 0. So go ahead and solve for those coefficients in whatever way you see fit. I'll go ahead and solve explicitly. 30a equals 12b. So a equals 12 over 30. Let's see, that is, I'll divide by 3 maybe. That gives me 4 over 10 Oh, could have divided by 6, would have been quicker, 2/5. Okay, so, oops. Let's not forget about our B here. All right, so now we have a relationship between A and B. I'll plug that back into the top equation. Minus 12 times 2/5 B minus 30B equals 10. I'm going to just multiply through by 5 to get rid of the denominator here. Okay. So if we multiply through by 5, we get a negative 24B minus 150B equals 50. So what do I have here? 50 is equal to negative 174B. So B is equal to 50 over negative 174. What does that reduce to? 25 over negative 87. That's a horrid number, but there it is. And then plugging it back up to solve for A. A is 2/5 of B. So 5 goes into 25 5 times. So we get a negative 10 over 87. So we've solved for A and B. I won't even write out that steady periodic function with the A and the B because I believe we want to condense. Yes, so we want a single cosine function here. So let's go ahead and utilize the fact that C is the square root of A squared plus B squared, which is going to be a 1 over 87 square root of 100 plus 225. So the square root of 325 over 87. All right, and I won't even reduce that for now. And then the other thing we need to look at here is finding the alpha value. So let's see, I have the A is negative. So that tells me that alpha is going to be pi plus tangent inverse of B over A, which is going to give me, see, 25 over 10, which is 5/2. So we now conclude that our steady periodic function is the square root of 325 over 87 cosine of 5t minus alpha, where alpha is listed up above. All right, so we've completed our steady periodic solution. Now we need to come up with the transient solution. Oops, and I just noticed that I have an error here. 25 squared is not 225. I thought that seemed a little low. That should be 625. So let me make that correction here. I'll write it in red so that you can see the difference. 625, which makes this 3 a 7. Square root is 725. So actually that reduces here to, if you want to pull out a square root of 25, 5 square root of 29. Ugly indeed. So I'll go ahead and just correct that here down below. Should be 5 square root of 29. My apologies for that error. Okay, so now we'd like to move forward finding the, what are we looking for here? The transient solution. So let's move forward. It looks like I'm going to run out of paper, so I'm probably going to have to open a separate page here to finish this out. I didn't budget my time very well. But you'll recall that what we had for the transient solution so far was an e to the negative 3t C1 cosine 2t plus C2 sine 2t. Now we know that the general solution is the sum of the transient solution and the steady periodic solution. So we want to add those two solutions together in order to come up with our general solution. Now, you will note that they only asked for the steady periodic and the transient solution separately. They did not ask for the general solution. So you might be asking, why are we even bringing this up? If we only need to find the transient solution, why would we add them together? Well, recall that we're still missing these coefficients. The only way for us to solve for those coefficients is to use these initial conditions up above. But those initial conditions are not conditions on just the transient solution. They're conditions on the general solution. So in order to solve for C1 and C2, we need to combine both the transient and the steady periodic solution and then impose those initial conditions to solve for the C1 and C2. So what I'm going to do is I'm just going to open up a new blank page here. And let me write out what I need. I'm not sure how to change this back to white, so I guess we're going to work with black here. So what I had for the transient, again, just writing it out one more time, e to the negative 3x C1 cosine 2t plus C2 sine 2t. And then we had our steady periodic. Now, I had condensed the steady periodic to a single cosine function because that's what the book asked for. However, taking derivatives of that is ugly because it involves that alpha. And so what I'm going to do is I'm going to intentionally rewrite it as the sum of two oscillations. So if you think back to what we had found for A and B, we had that A was negative 10 over 87 sine of 5t, and then B was negative 25 over 87 cosine 5t. All right, so I am intentionally writing it in this non-reduced format. And the reason why I'm doing that is because now when I plug in 0, the sine function will die and the cosine function will go to 1. If I leave it in the reduced format, although the derivative is easier to compute, when I plug in 0, those functions no longer go to 0 or 1. And that's not a good thing. So let's take a look at the general solution by summing these two together. All right, so our first initial condition was the following, that x of 0 is 0. So let's go ahead and just plug that in. The exponential function goes to 1, cosines all go to 1, sines go to 0. And so leaves us with this calculation. So we've now concluded that C1 is 25 over 87. Okay, good. There's one of our answers. Excuse me. And now let's take the first derivative. Note that we will have to use the product rule here for this first term. So the first derivative, get this to hold still. Goodness, there we go. X prime of t. My hand is making everything bounce around. There we are. All right, x prime of t is negative 3e to the negative 3x. leave that entire set of parentheses untouched. And now I have e to the negative 3x, taking the derivative of the inside terms. I have a negative 2c1 sine 2t plus 2c2 cosine 2t. And now taking the derivatives of the last two terms, I get a negative 50 over 87 cosine 5t plus 125, what I wanted to say earlier, over 87 sine 5t. Now, the initial condition I'm going to use here is that x prime of 0 is also 0. So when I look up here, all of these sine terms are going to go to 0. The exponentials go to 1, so I get a negative 3 times c1 plus 0, and then plus 1 times 0 plus 2c2, and then minus 50 over 87. All right, so what I have is 50 over 87 equals negative 3. I know what c1 is. It's 25 over 87 plus 2c2. All right, so I have 50 plus 75. 125 over 87 is 2c2. So c2 is 125 over 14, carry the 1, 174. All right, so this is enough. We can now state our transient solution. We had C1 up above here was 25 over 87, and that was the coefficient of, whoops, I forgot my exponential. Let's put that first. So that's e to the negative 3x. And then our C1 is 25 over 87. And we had cosine of 2t. And then plus 125 over 174 sine of 2t. All right, so here is our solution for the transient function. All right, and that concludes section 3.6, forced oscillations and resonance. I look forward to answering your questions in class.